So hello everybody and welcome to the Igneous Petrology Series Lesson 5. In this lesson I'm going to be talking about binary solid solution phase diagrams. So let's get right into it with some terminology. So solid solution is a miscible mixture of two solids. The liquidus represents the temperature above which the entire system is liquid. The solidus represents the temperature below which the entire system is solid. Equilibrium crystallization or equilibrium melting means that the system remains closed during either crystallization or melting, where the crystals and the liquids remain in equilibrium with one another. Fractional crystallization or fractional melting means that the system is open, and it means that liquids and crystals within that system can be decoupled from one another. Now, fractional crystallization, for example, can be completely or intermittent. So in complete fractional crystallization, crystals are removed the second that they're formed from the liquid, and then they evolve separately. Whereas in intermittently, we crystallize a few, say, olivine grains, for example, and then we remove them. We then crystallize some more olivine grains, then we remove them. Rather than that instantaneous removal, we essentially remove blocks of olivine in bulk. Okay? So, now we're looking at a phase diagram of olivine. On the left side of the x-axis, we have 100% phthalate, i.e. 0% forsterite. And on the right side of the x-axis, we have 0% phthalate, i.e. 100% forsterite. Now these two phases are in solid solution with one another, and in the middle here represents a certain percentage of phthalate to forsterite. So here, for example, we have 60% phthalate and 40% forsterite, so on and so forth. Up the y-axis, we have temperature. This line here represents the liquidus, so anything above here is 100% liquid. This line represents the solidus, so anything below here is 100% solid. Anything between these two lines is a mixture of liquid plus olivine crystals. If we envisage a point here, this is now sitting in a divariant field if we think back to Gibbs phase rule. So that means I'm going to have to define the temperature and the composition to know exactly where our system is. So let's say around 1850 degrees Celsius, and here maybe around 51% forsterite, 49% phthalate, something like this. As we cool the system, we're going to hit our liquidus, and when we hit the liquidus, we're going to crystallize our first olivine grain. And it's going to look something like this. So here we have our magma at liquidus, or we can call it olivine supersaturation, okay? And we're going to crystallize an olivine grain with a forsterite content of 80. So if we draw a line on our phase diagram down from where our first olivine crystallized, here we have 80% forsterite, 20% phthalate. That's this guy. Now, as our system evolves, it's going to do something like this, okay? And then it's going to look something like this in the diagram to the right, okay? So, I've just drawn a tie line here between the two, and then two lines down from where our olivine currently is and where our liquid currently is. So now we have our magma crystal mix. We still have our olivine there, because this is equilibrium crystallization in this example. We still have our olivine there, which still has a forsterite of 80, but we've also been crystallizing olivine anywhere now between 80 and 60% forsterite, represented by this olivine grain here. If we think back to the last lesson in the lever principle, it's going to look something like this, right? So just like our seesaw, we have our fulcrum point here. So we do 49 minus 27, 49 being the line down from our fulcrum, minus 27 over 65 minus 27 means that the system is currently 50% solid or 43% liquid. So pause the video now if you wish, and you can use that equation from the lever rule lesson for liquid. So calculate using the other calculation and see if you get the same results. So let's continue to evolve our system. So it's going to do something like this, and now we're at 100% solid. So the last remaining liquid exists somewhere like this. Let's say around 85% phthalate and 15% forsterite, something like this. So that means all the olivine grains that crystallize in this system exist in this compositional field. So we've crystallized during the evolution that I've just shown you anything between forsterite 80 to forsterite 49. There. Brilliant. So let's do something a little bit more complex, and now we're going to look at fractional crystallization. Equilibrium crystallization is great to get the idea behind the concept, but it very rarely happens in nature, and often things like fractional crystallization are more dominant in geological systems. So if we take a point now existing here, So if we cool that system, we hit our liquidus, we crystallise our first olivine grain at around 93% forsterite or 7% phthalate, which is the most forsteritic they can be in geological systems, and also our liquid that's housing it. Our system's going to evolve, and you can pause it here, apply that lever principle if you want, and see what kind of calculations you get. I'm not going to do it now because you can refer back to the last slide, but give it a go. So this is what our mixture looks like right now. We have our magma crystal mix. Now what we're going to do is we're going to remove all those olivine grains that have crystallized so far. So now we're left with a liquid with around a forsterite content of 58% or a phthalate content of 42%. So what we're going to do now is, because those solids have been removed, our system now exists where our liquid is. So we're going to evolve now from this point. So we're going to do something like that. Okay, and again, you can pause it here, apply the lever principle, because it looks like we have perhaps a bit more solids here because this arm is longer, and a bit less liquids here because this arm is shorter. Okay, and then we're going to remove all the solids again. We're going to evolve down again until now we're 100% solid. And then all's happy. And what's interesting, so as you remember in equilibrium, the green triangle, or our system in this case, exists on the same line all the way through the system. So it starts here, evolves downward, and ends here. Whereas you may have noticed in fractional crystallization, our triangle started here, but now it's ended down here. Okay, so the system has evolved, it's changed composition. So thank you, I hope you found this helpful. If you did, please stay in the loop by clicking subscribe. Any questions or suggestions, drop them in the comment box below. Thank you.